The broadcast is now starting. All attendees are in listen-only mode.
Good morning, everybody. Maybe I should say good afternoon or maybe good evening wherever you are. Welcome to the second KARALIT webinar on how KARALIT is transforming the computational fluid dynamics, or you might say CFD world. My name is Al Grefa, and I will be one of the two presenters today. As I said, this is the second webinar following the webinar that we had a few months ago focused on CFD valves. Today, we will focus on something different, and we will do some CFD for internal flows. So during today's webinar, we will go over an overview of our company, KARALIT, and the innovation that brings it. We will then see a live demonstration of the software capabilities, and this session will be done by my colleague Sohail Alizadeh. And we will end up the webinar with a recap session in a few minutes for questions and answers. Let me do some housekeeping before starting. All participants are on mute, meaning that your voice is not heard. However, you can submit questions to the presenters. And if you want to submit a question, just please use the panel on your right side. Type in the question. We will try to address all the questions during the webinar and also along our presentation demonstration. In addition, we will also record the webinar and make it available on our website at www.karalit.com. Okay. Let's start with a few words about our company, KARALIT. KARALIT was born as a spin-off of an Italian research center called CRS4. It's based on a beautiful island of Sardinia in the Mediterranean Sea. The founder, Marco Mulas, led the fluid dynamics group at CRS4 for about 20 years. Developing and using the very same core technology that you will see today as a part of research and consultancy. So you will see that although new and young, the code has been used for quite a good number of years in various projects with code that has been already validated and proved. The company is entirely private, with private investors. The headquarters are in Sardinia, exactly in Pula, that is close to Cagliari, as a big city is Cagliari. We have sales offices around the world. We have it in Milan, in Italy, London, obviously in the UK, and Cary, North Carolina, for the North American market. So, why KARALIT? So let me try to ask you a couple of questions, okay? Can you imagine setting up a CFD in a few minutes rather than hours or maybe days? So that's my first question to you. Well, with KARALIT CFD, you can do it because KARALIT CFD eliminates the meshing stage, saving up to 99% of the user preparation time. And this is due to the use of the immerse boundary method, a technology that is unique among commercial CFD software. Let me ask you a second question. Can you imagine having any design engineer, not only the most expert in CFD, the guru in CFD, but any design engineer doing CFD along the design cycle, improving and testing and validating various scenarios, various configurations? Well, the answer is there. Again, KARALIT CFD can do it, as KARALIT does not require any in-depth CFD knowledge because the use of a customer-specific apps that makes it extremely easy to use. Today, we will see during the demonstration an app developed for internal flows that is geared specifically to design engineers. For instance, today for engine designers or biochemical engineers. just to support their design flow, their specific design flow and validation. So KARALIT CFD brings 3 new, fresh, and powerful ideas to the market. Our marketing department likes to call it KARALIT revolutions. And those 3 concepts are, number 1, it's a new technology based on the immersed boundary method that leads to no more meshing. Very easy concept. The second one is a new approach to interact with the user with easy and highly customized app to address your specific application, requiring only the necessary input for that specific workflow. Again, only the necessary input for that specific workflow. For instance, the app for internal flow simulation that you will see today requires only specific inputs for internal flows and has, for instance, mass flow as a parameter for the convergence, while if you're dealing with an external aerodynamics simulation app, for instance, for a car, well, you have different set of inputs. 3, our pricing structure is very simple with no hidden costs. There's only one price for the software, and we do not charge by the number of processors you use. You can use 1, 10, 1,000, I heard 10,000, 30,000, 40,000, as I heard some customers have, with the same price. So you can leverage your existing computational capabilities at a fixed budget. I said it before, KARALIT CFD is based on the immersed boundary method. So the question is, what is the immersed boundary? Well, let me give you a 36,000 feet overview. The immersed boundary is a method that has been around for about 20 years, but so far there are no known commercial CFD applications that use this revolutionary approach. A body, being a curve or a surface or a solid, whatever you have in your CAD system, is immersed in a Cartesian grid where all the cells are rectangular. The detection of where the fluid is, inside or outside, is done automatically. So great application for immersed boundary methods are moving parts, very complex geometry, and because you don't need to do any meshing, it becomes a very easy tool to use during the design process and design optimization. When compared against traditional methods, either structured multi-blocks or unstructured mesh or hybrid, the immersed boundary offers a mesh that is automatic, fast, and based on a rectangular and regular grid. And this compares with mesh generated by traditional methods. They are manual, tedious to generate, days and hours and days and weeks, and often with cells that are deformed and distorted, compromising the quality of the cells per se, okay? Before going to the live demo, let me anticipate what is the easy workflow for KARALIT that you will see in a few minutes. And this can be summarized in 3 main logical steps. Step number 1, import the geometry, such as solid, in a STL format. That's step number 1. You have a CAD model, you export it in an STL format, and we read it in. Step number 2, definition of the simulation parameters, like fluids and boundary conditions, making use of the selected and specific app. That's step number 2. parameters definition. Step number 3, run the simulation. Now, and then at the end of the simulation, you can review results such as velocity, pressure, temperature, and those values are available to be analyzed, displayed, and documented. So that's the KARALIT easy workflow. We call it 1, 2, 3 steps. Okay. I think at this point, let's go to the live demo portion and have Suhail showing us the power and the simplicity of KARALIT CFD. Suhail.
Okay, thank you, Alberto, for that introduction. As Alberto mentioned, we'll be having a look at, in this webinar, a couple of examples of showing basically the simplicity of the KARALIT code in the internal internal flow setup environment. We've got an application for internal flows, and we shall be using that. Essentially, the first application is that of a mixer. I will just bring up the CAD geometry for that and talk around it a little. As we did in the previous webinar, we will just show the case being set up from scratch in this live demo to show essentially how easily one can set up an application using KARALIT. So I'll just call this case test mixer, and open up the application essentially. So I go into my KARALIT window here and set up an internal flow application and read in the surface for the mixer. That's what it looks like. It's called a multi-inlet vortex mixer. A vortex mixer because it's got a number of inflows into a central domain causing a vortex and one outlet at the top. Essentially, it's used in the biochemical industries to achieve a homogeneous mixture at the outlet for organic or inorganic compounds, and the quality, the solvent quality at the exit, the solvent quality that is achieved eventually, it is very much dependent on the mixture, homogeneousness of the mixture at the exit of the mixer, and that is controlled by the inflows, for example, the velocities at the inflows. Right, so what we have here is just the CAD, the STL export from the CAD model, and we will bring that in to KARALIT and look at it essentially in the preview window. As mentioned, we are in the internal flow application. So also, as you can see, in this internal flow application, the geometry has been immersed automatically and fitted to a rectangular Cartesian block. So that automatically fits around the object. The user doesn't have to do anything about that. One can choose the level of coarseness or fineness of the grid. I've just made it a little bit finer, and you can see that the view changes and we've got finer meshes. in that block, in that central block where the geometry is immersed in. Following that, we just need to set up the inputs and outputs to the domain in this menu as well. And we do that with a submenu here, where we can choose the boundary condition regions, for example, 1. There are a total of 5 of them. And we just keep adding, perhaps add the outlet as well, and so on. And there's one last one of the inlet to add in as well. Right, we can save that and go back to our internal flow application screen. And you can see here that all of those inputs and outputs are selectable, the boundary conditions, and one can choose from a choice of boundary conditions. One thing I like to just point out here is that KARALIT automatically puts at the inflows and outflows circular extensions. That's essentially in order to ease the application of boundary conditions in the code. They are automatically done, and the user doesn't have to do anything with it. And essentially, it's a cylindrical mesh, which is interfaced to the regular Cartesian mesh of the central immersion block. And there is no way that these pipes can actually interact with one another in the solution either. It is just a tool for setting up the boundary conditions. So the code does that. We don't have to worry much about that. I'll just use the identifier of those pipes in order to see what is the direction and for the velocities that I need to put at the boundary condition. So boundary condition 1, x is in the negative direction, and I would like to put velocity and temperature. So if we put x is actually at minus 10 meters per second, and the temperature is either 320 or 300, depending on which pair you're looking at. So that's for that one. Then number 2, if I remove that, that one is number 2, and x there is in the positive direction. That's fine. And there I need to set up also as 320 Kelvin. And number 3, that's around the other side. We've got the flow is in the y positive direction there. So x becomes 0, y becomes plus 10. And here the temperature is actually around 300 Kelvin. And let me see, was number 4, and there y is in the negative direction. So just a few inputs for the boundary conditions, and there number 5. Actually, we would just like to set that up as pressure and at 10 to the 5 pascals. So that's all that we do actually in terms of the domain creation and boundary condition specification. That is all that's inputted. The next panel to fill in is for the fluid properties and flow conditions. So the flow there is basically is a turbulent flow. We're going to use the Spallart-Almaras model. There are choices of K omega and KG models to use as well. We shall use the ideal gas equation, and here in terms of the initial settings, the flow inside the domain actually, whilst it comes in at about 10 meters per second, it's a large volume inside comparatively to the inlets, and it reduces quite substantially. So it actually is about around about 0.1 meters per second in magnitude. So we can then pressure and temperature. I think we can put 300 Kelvin and 1.2 for density. Okay, and we would also like to use, it's a density-based solver, so at low velocities we use preconditioning, and the level of velocity is set there as well. And we would monitor the progress of the solution using the energy equation residual. That's pretty much all set as well in terms of the fluid flow properties and the fluid conditions. Let's just save that. And thereafter you go to the simulation. You have a choice of an explicit or an efficient implicit solver. And you can choose your under relaxation, your discretization schemes, and the number of iterations to solve. CFL, the code is pretty robust in terms of the efficiency of the solver, and one usually can cope with fairly high CFL numbers in order to get convergence pretty quickly using the implicit solver. And these are the essentially the dumping frequency for the solution file and for the log files. So saving again, and there is a choice of actually two post processors, TechPlot and Nsight, which are both quite renowned post processors, and we will show the results using both of them in application. So I've outputted to both of those files for now. That's pretty much all done, and we come out into the run window again, and the only thing left to do is to push the start button. Of course, one needs to let this run, for half an hour, 1 hour, in order to get convergence for this calculation. It's a fairly coarse mesh, and in the webinar we don't have time for that. But I just wanted to show you how quickly it is to set up this calculation from scratch, and in the space of a few minutes you can be in a position to run your model. And please also note that we haven't actually generated any mesh. This has been automatically done. The block mesh is automatically done by the code, and the immersion and the intersection and the imposing of the appropriate boundary conditions in the immersion block, where the body cuts through the background mesh, is all done automatically by the code. We just set up a few parameters associated with the density of the mesh, as you saw in the immersion block. So I've run this case previously, and what we can have a look at is essentially in the output window you get initially a summary of your setup, and you get a reporting about the immersion procedure, the immersion being the body the geometry being immersed in the background block, and the intersections and all to do with boundary conditions being taken care of automatically by the code. Then after that, just like any other finite volume solver, an iterative process starts where you're solving the conservation equations, the linearized forms of those equations in an iterative fashion. And here an implicit solver is used, and as you can see, within about 1,000, just under 1,000 iterations, of order 3 to 4 magnitude reduction of residuals is achieved. We can look at that. That's the plot of the residuals. It's a very monotonic drop in the residual for energy here, as was said. And additionally, in the monitors, you can look at integral quantities. They are accessible within the KARALIT window itself, like mass flow at the outlet and through the various inlets. As an indication of convergence, those 4 inlet mass flows would sum up pretty exactly, to the outlet mass flow. And as you can see, it has nicely plateaued out, indicating convergence again, and also values like other integral values like pressure. Let's have a look at, in TechPlot, for this case, the solution, the results of the calculation. Just to see what the flow field and some of the outputs look like, some of the key output data looks like. Here I've put in streamlines through 2 of the inlets, and as you can see, there is a vortex inside the mixer generated, and mixing takes place within the body of the mixer using the mechanism of that vortex, and flow comes out axially through the top output. Looking at some of the parameters, velocity vectors gives us an indication of what the flow field looks like inside the mixer. On top of the streamline values, we can move that plane and see how the velocities actually change direction as you approach the outlet. Inside the core of the mixer, a vortex is induced. Looking at, let me just bring that plane of the velocities a bit higher so that we can see velocity magnitudes. So as you can see, the velocity in the core, speeds in the core of the mixer are pretty low, as we had put in the initialization, around 0.1 meter per second. Whereas at the inlet, they are much stronger. Turn that off. Look at temperature. So here we see that 2 of the inlets are at a higher temperature compared to the other 2. And if we move that slice towards the outflow, you can see a temperature is an indicator of the uniformity actually of the mixture there. So it's doing its job nicely. Coincidentally, the paper written on this mixer suggests that the CFD is in quite good comparison with the test data that they have in one of the universities in the States. Looking at phi, a scalar, a passive scalar, that's a scalar that does not contribute to the properties of the fluid in the domain. It's just carried by the flow field, so it doesn't impact the properties of the flow. Suggests again the nature of the mixing inside. And if we go to one more tab, we can see a measure of the turbulent viscosity, which helps us to understand where are the highest mechanisms of shear, and hence you would think that that is where most intense mixing is taking place. Okay, so let me just come out of that now. As you've seen, using this example, we showed how easy it is using the internal flow application to set up very quickly without the need to do any meshing. Set up a quick CFD calculation and prepared for a run, and within the space of an hour or so, one could be looking at the results had one started the run and allowed it to continue that we were looking at. So the second example that I would like to look at in this webinar is that of a motorcycle cylinder head. That is a courtesy of University of Salento, who have provided us the geometry for that. And we've got a simplified version of the geometry that we shall look at here. Essentially, we set up a new case again. I've called it test head for the motorcycle head, cylinder head, and set up an internal flow STL input application. And we bring in the surface again. That's again the CAD surface, which is just immersed into the background Cartesian mesh in KARALIT. This CAD surface is output from your standard CAD package, and in KARALIT we read it in STL format. It's read in STL format and immersed. So what you have here is a 3-cylinder motorcycle engine. There is inlet of the air into the cylinder head. It's an interesting design because the air comes in and as it can emerge through different ports into the cylinder, and prior to that it is mixed with charge, with fuel, and what one would be looking for is the efficiency of the combustion in the cylinder head, given the arrangements of those ports and the openings of the ports relative to one another in the cylinders as well. So the numbers, the geometrical arrangements, the openness of one cylinder relative to the other is all going to impact the flow distribution and the flow of the charge into the cylinder head, which is all going to impact the nature of the combustion. So here, I guess the uniformity of the flow, the maldistribution of the flow field through those ports, all of those are of interest. Okay, as before, we can save that into our KARALIT case now. We've read that in, and as you can see again, the block, the immersion block, arranges itself automatically, sizes itself automatically to the domain, to the geometry that's read in. We've got a fairly coarse mesh actually at the moment. It would be useful to refine that a little bit. Okay, so as you can see, we've got quite a few more cells in there now. It's still a coarse mesh, but it's indicative of, as a starter, of what the flow field might look like. You know, as you can as you can see, you can easily go back into, once having done one calculation for mesh dependency type calculations, you can easily go back, change the density of the mesh here, rerun, and compare to your previous results as well. So mesh dependency is really trivialized, using immersed boundary in KARALIT. Okay, we've done that. As before, we need to go back, go into the boundary menu and set up the boundary regions initially. Okay. So perhaps number 1. Okay. And as before, you would, I'm going to add the 4 inlets like I did with the mixer. Here they would be the outlets. So I'm not going to go and basically choose the other ones. I'm just going to save it at this point and come out. But you can see how quickly one can set up the regions, come out, and basically through my inlet,
I think we lost the Sohail because I cannot hear it anymore. I'm sorry. Let me see if I can. Hello, Sohail. Sohail, I think we lost you. At this point, I think for some technical issues, we lost completely our presenter. And so I will go ahead and complete the presentation. If Sohail comes back, then I will give him back the few minutes so he can complete the demonstration. So I apologize for this inconvenience. I'm not sure where the technical issue is it from our provider or let me go ahead a couple of minutes in advance from our timetable. But first of all, I want to thank Sohail for the nice and exciting presentation that we have seen so far. I think that clearly you have seen the ease of use of KARALIT CFD, where, with the 3 simple and logical steps, you can set up and run a simulation. Again, you have as an input a CAD model. The second one is you just specify some parameters like the fluids that you're using, the boundary conditions you're using. And the third, you just run the simulation. And obviously then you have all the parameters like velocity and temperature available for your engineering study. Okay.
Hello, Alberto?
Oh, you're back.
Yes, yes.
Oh.
I saw that it has taken, you took the control back.
Yes, because you disappeared with the voice.
All right. I was seeing a message coming up saying that it is trying to reestablish the connection.
Okay, so
shall I continue from here on?
Sure. Let me go back. Apologize for this technicality, and I will give back the control to Suel so he can finish the his demonstration.
Okay. Thank you, Alberto. Well, you know, in a live. Thank you, Alberto. In a live demo, you always have surprises. But essentially,
it always happens, huh?
Yeah. What I've done is to set up the computational domain for the second case, the motorcycle engine head. We've set up the boundary conditions, and we went through the setup of the computational immersion of the geometry into the background mesh, which is all automatically done apart from a few setup parameters to essentially achieve the resolution of the mesh. Now we are finishing up with the setup of the fluid panel, which has got the flow conditions. It's a turbulent flow and some of the flow properties. Ideal gas equation is applicable here. It is actually a compressible flow. Flow turns out to be of significant Mach numbers through the small ports. So that's pretty much it, and we can monitor here perhaps the X momentum or the Y momentum, doesn't really matter. And lastly, one would just go and set up, like before, the calculation with the implicit solver, setting the number of iterations and the dump velocities, dump frequencies of the log of the iterations in an output file, and also of the solution, dumping of the solution. So one would say that, so as you can see again, there is no meshing involved, and pretty much all of that is taken care of by the code. And at this stage, one would just press the start button and wait for a few hours, a couple of hours, to achieve a solution. As you can see, these two examples have demonstrated the nature of the KARALIT direct workflow process, where we are trying to connect directly with the design, with the CAD output through the facility of the immersed boundary technology. We take the output from the design and immerse it directly into the tools of our code and achieve a CFD setup pretty ready, in a very ready fashion. Looking at the results of this that I've run previously, over 3,000 iterations, convergence for that, again, it's pretty good. You can see the Y momentum here after 3,000 iteration having dropped, you know, to over 5 orders of magnitude. I mean, that's pretty astounding, actually, in terms of a convergence performance. It shows how efficient and how robust that implicit solver is. And we can look at the integral quantities of mass flow and pressure, and you can see them having plateaued out. Indicator of the convergence again, the steady state convergence of the code, and outputting quantities which are appropriate to this application. In this, the results of this, I would like to look at the other package, Insight, which KARALIT output can be viewed from. Here we've got basically the cylinder head again, and I've done streamline plots from the inflow. Insight is actually a pretty intuitive post-processor, and you can do things very interactive with it. So one can pick the inlet streamlines and move it through the domain, and as you move it to the domain, you can pick up different streamlines within the domain, and it shows you essentially it's an indicator of the pattern of the flow field. So here you can see how the flow field is distributing itself and how it is finding itself through those exit ports. With Insight again, one can, for example, plot out the velocity field in the domain, and you can actually rescale the velocities, picking out interesting features in the domain. At the color scale, one can easily actually rescale the heads as well by picking them and rescaling, looking at some particular features in the domain that one might be looking for example, regions of recirculation. Then again, one can do contour plots as well, and here I've got a contour plot of temperature set up, and as before you can just pick on the scale and change the color there, the range of that scale, and it interactively impacts the contours. And also you can also change the density of the contours as well interactively. So a very interactive tool really for viewing and post-processing one's results. Okay, at this point I would like to hand back to Alberto for a recap of what we've done, and thank you for your attention, and basically await your questions. Thanks very much.
Okay, Shreya, thanks again. I already thank you before when you got disconnected, and thanks thanks again for the exciting demonstration that you provided us today. Before I was summarizing the three major steps of our KARALIT direct workflow. That I'm going to summarize it again, just to complete it. Again, step number one: bring any CAD geometry that you have already specified inside your CAD system. We import an STL. Step number two: select the application that you need or that you're going to use, or we call app. Okay, everything now in these days, everything is an app. You know, iPhone, iPad, everything is an app. We also have app where you're going to use also. You are going to define free properties and simulation properties, and then at the end you just run the simulation, and then you can review the results either with standard visualizers like TechPlot or Insight, as Suhail has shown us. Okay. I do understand, and I hope to answer some of the questions that came through. You know, during the demonstration, basically you have seen that Suhail used a regular and constant grid for the two parts that he used for this short webinar. Also wanted to remind you that of other cases where a local grid refinement is necessary, such in the case of this racing car shown in the left side. and this is courtesy of Tattoos Racing. And in the, for instance, in the case of a ball valve, where there are small holes for calibrating the flow. Okay, so those are other examples of applications that maybe next time, maybe next webinar, we can see a little more in detail about those examples. So before opening the QA session, let me summarize the 3 major values of KARALIT CFD. Number 1, no more meshing. Remember that. We don't do any meshing. XOIL didn't show any meshing at all. Number 2, it's an easy and streamlined setup that is app-based. Depending on what you do, if you do external aerodynamics or internal flows or valves or buildings, built environment, and so on. Number 3, a price structure that allows to leverage your existing hardware and computation capabilities with no hidden costs. Okay? So what if you want to learn more about our evolutionary CFD software? Well, what you can do, you have different routes. Number 1, you can visit our website, www.karalit.com, Karalit.com. Over there, you can download the free 2D version. It's downloadable from our website. There's no time limit. It's yours to keep it forever. The 2D version is very similar to what you saw today, the 3D version. The only difference that rather than handling solids, you have to handle 2D geometries like curves. Obviously, you can contact your local sales office if you are in Europe, either Milan or London. If you are in the Americas, so you can contact the American office here in Cary, North Carolina. Number 3, obviously, these days, the email is the best way to reach our sales organization. And so send an email to sales@karalit.com. But remember, this is the second of a series of webinars, so I would like to invite you to stay tuned for the next webinar. And we don't know what we are going to do. We are coming up with some ideas. Maybe you can suggest some ideas. So at this point, I would like to open the QA session. Please use your chat window on your right side to submit the question. And let me see some of the questions. We had a lot of questions, and few of those have been already answered. I'm going to pick some of those. We are kind of tight time-wise. One question I had is it possible to test the software for our company to initially see the benefits of this software for our organization? Absolutely. So as I said before, you can start with a trial version of the 2D, where again, same workflow, same capabilities. You can see how easy it is to use the software. All you have to do is that you go to our website, you register, obviously, and we will send you a link to download the software. Okay. If you are interested in 3D, then I would ask you to just talk to your local sales office, and they will be happy to to accommodate your needs. Another question. Well, we have tons of questions. So first of all, let me tell you that we cannot answer all the questions that are coming through in this time frame. Few questions have been already answered. We will follow up one-on-one, and we provide you with the answer in the next couple of days. Okay, we will send you the question, and then also if you want an open communication. One question is, and I'm picking here, when will be the 3D software available? Well, what you have seen today is an available version. What Suhail showed is an available today version of the software. So all you have to do is just buy the software and download it from our website. Okay, so the 2D version is free, available, no time frame. The 3D version is available, is a commercial version. You have to, obviously, you have to pay for that. I have a questions. How exactly does the customized version of KARALIT works? Is there any general purpose option of setting up CFD problem? And Ravi, let me try to understand your question, and I will try to answer you, and hope to answer you correctly. Otherwise, you can feel free to follow up in the future. We can, more than customization, what we are talking about here is, I would say, is extending the capabilities, the standard capability of the shelf of KARALIT. And the way you can do it is that a customer can extend the capability just by writing their own code for instance, for the turbulence model. I think Suhail mentioned the fact that we are supporting three models out of the box: SA, Spallert, and Almaras, KG, and K Omega. But if you have your experimented model of turbulence, what you can do through our open code functionality, you can write your external scripting, and you can integrate it with our standard package, so that the turbulence model used is going to be your specific turbulence model. I hope that I answered your question. Similar to that, the open code also, through the open code, what you can do is that you can also write your own equation of state. We provide two equations of state, one for compressible and one for incompressible. But you can write your equation of state if you desire so, okay? Or maybe you can write your through the open code. You can write a different scheme for a simulation. Let me. And again, I hope that I answer your questions, Ravi. Please feel free to send me follow-up questions. Another question that I have is, can you provide me any reference about the mesh-free method that you are using? Absolutely, absolutely, Stella. I can provide you with a list of I don't know, there are a lot of papers about the immerse boundary method. It again, as I said before, immerse boundary method has been around for about 20 years. So there's kind of a 20 years of experience, and most important, 20 years of papers focused and around the immerse boundary method. I will send you a list of papers so you can download them. There are you can go to the website, you can Google them, but I will send you a list, and I hope that you, Stella, send me your right email address. Okay. So it's 9:59. We are 59 minutes inside the webinar. Well, all I want to do is I want to thank you. I want to thank you for your time. And what I want to do, I would like to see you at the next webinar that we are going to have, and looking forward to further talking to you directly. Remember that we are going to put this recorded webinar on our website, so please check our www.karalit.com for a recorded version of this webinar. Again, thank you very much and have a great day or maybe great evening. Thank you. Bye-bye.